And I want to talk to you about something that should have dawned on us and didn't. And I brought it up once, and to be quite frank, I took a similar class as what you're taking right now. I remember getting to this point in that class. I remember the teacher saying this, and in my head I kept thinking, well, yeah, I guess so. That would have to be true. But at the same time, it took me quite a while to wrap my head around this. So I don't think this is something that happens easily, especially considering some of the constraints we've had in the last couple of weeks in talking about the direction of flux and the direction of induced currents and all that kind of stuff, which has caught some of you, in a difficult position to try and figure out what's really happening. I want to emphasize something that I've tried to say from the very beginning of the year, or at least beginning of this unit, that nature behaves in a specific way, and it tends to be about the flow of energy, or the flow or the passage of inertia and momentum. In circuits, we tend to not think of inertia the same way, although I've talked to you a couple times about the concept of inertia in a circuit, that there seems to be something here that attempts to mediate the flow of energy or create a time constraint. It was easy to see that when charging a capacitor, that you could adjust how long it took for a capacitor to charge. And we talked about the time constant, we proved it with the differential equation, all that kind of stuff that we did ultimately to show that it takes time for a capacitor to charge and that you can adjust that amount of time. When we started getting into started getting into Faraday's law and the generation of induced current, I tried and probably failed for some of you to impress upon you that you don't get something for nothing, that energy comes from somewhere. We have this idea that electrical energy is free, and you feel that way right up until the moment your phone batteries run out, and you're frustrated that you have to charge it again. In fact, some of you will say, I need a new phone, my batteries just don't stay charged as long anymore. Under those circumstances, you get the point that perhaps there is a finite amount of energy, but then you don't see that energy, you just plug it in someplace. You're constantly pulling down my power plug so that you can plug something in that you forgot to charge last night, right? And understanding it, but it's almost as though it's free. Well, it's not free. It's coming from somewhere. The energy isn't just happening. And whether we spent the entire beginning of the year talking about having some kind of voltage source, and that our voltage sources stored the energy previously. So the battery was charged up through some other process that separated charges or used some kind of fuel that continuously separated charges. So a standard battery, that's what it's doing. It's an acid redox reaction. Eventually the fuel will run out and you'll have to go get another battery. But that was done previously, meaning the energy came from somewhere to create that battery. And now that you're using that energy, sometimes we feel as though it's not coming from somewhere. So then when we talked about EMF, we talked about the physicality of where the energy comes from. Something was moving, the movement of that particular thing caused a separation of charge and therefore a current. We talked about motional EMF. And that created some conditions for us that were tough. And a lot of you still suffered with your right-hand rule, trying to figure out the direction of whatever would be occurring. But we could, even without Lenz's law, come right back to whatever the direction of the force is, it's got to be to try and prevent the creation of this electrical energy. Before you even throw down your right-hand rule and try and figure out the direction of a current or a magnetic field, the direction is trying to prevent there being the creation of electrical energy, because status quo to be maintained. So you always knew the force in the bar was going to be preventing that whole thing from going into the magnetic field. And the force in the bar is going to be to prevent that loop from being pulled out of the magnetic field, regardless of the direction of the magnetic field. That part didn't matter. If you're going to be creating a current, then things were going to have to require work to be done. And in the case of motional EMF, it was physical work. So you guys had a problem yesterday, both of you, whether you were group A or group B, and there was two different problems on the test. One of them was about a wire loop entering a region of space with a magnetic field. One of them was about two rails and a bar being slung across those rails. Didn't matter which one you had, the force on the bar and the force on the loop would have been to try and prevent it from entering or exiting the magnetic field, regardless of what direction everything else occurred. Because you're not going to generate an electric current without taking that physical work from someplace. Now, what we're going to talk about here is something that never even occurred to me as a student of physics as well. And I didn't take this until I was in college, and I didn't take this particular class until my second year of college. So I was a couple years older than you, but they didn't have AP physics in the town I went to school. So I had to wait till I got to college for all this fun stuff. When you close this switch, there will be a current created in this loop, correct? What will be the direction of the current created in this loop, clockwise or counterclockwise? Clockwise, based on the direction of the battery alone is how we determine that, with the positive side, negative side of the battery. So there will be a current directed in this loop. We tend to think of that as happening instantaneously. The moment we close the switch, there's an electric field, and that electric field should be everywhere within the confines of the metal conduit that connects the one side of the battery to the other side of the battery. That electric field acts on all particles immediately and starts a current what we feel is instantaneously. It's not exactly true. I want you to think about something for just a minute. The moment I close the switch and there's a motion of charged particles, what else must be created the moment those charged particles begin to move? Has to be a magnetic field. In what direction? If we're looking at this particular loop, we can talk about what's happening inside the loop versus what's happening outside the loop. Let's focus on inside the loop. What will be the direction of the magnetic field created inside this loop? Into the board. So we will get a magnetic field into the board due to the closing of the switch. So before we closed the switch, there was zero flux inside this single loop of wire. When we closed the switch, the flux changed, correct? Well, when the flux changed, an EMF should have been produced in the loop. And the direction of that EMF should have been to oppose the change in flux, which means everywhere around this loop, there had to be an EMF generated causing a current in this direction to try and prevent the change in flux. This is sometimes called the back EMF. It tries to prevent the establishment of a current in a single loop circuit or in any circuit. Now, it's hard to imagine this back EMF considering we've made many a circuit and nothing seemed to stop the lights from lighting up, correct? So clearly this back EMF doesn't hamper our ability to create a circuit, but it's acting on our circuit every single time we attempt to turn on a light or turn off a light, because the reverse is going to happen too. I want you to imagine once we've established a steady state in our circuit. Once we've established a steady state in our circuit and our switch has been closed for a long period of time, there will be an established magnetic field into the board, just like before. When we go to open this circuit, there's going to be an EMF produced in this loop to try and prevent the change in flux. So the moment I try and open this switch, we're trying to stop there from being a magnetic field. Well, that suggests an EMF in the direction of the current that's already there to try and prevent this change in flux. Although the word back EMF would be associated with that as well, it's really an inertia for the circuit. It tries to prevent the change in the current that is there, or prevent the establishment of a current if there isn't one there. That's what we consider the back EMF. Now, I'll stop for a minute. I want to discuss this a little bit, but this back EMF is often known as inductance. And inductance is something that you can, if you're careful, find a way to develop in your circuit. Obviously, a circuit that has just a single loop in it probably isn't going to generate very much back EMF. I mean, we have a single loop, small magnetic field. So the introduction of Faraday's law here, and the things we know about Faraday's law, probably aren't being enhanced here. We know that if you want to enhance things in Faraday's law, a couple of ways to do those is to focus that magnetic field, try and create a larger magnetic field, and try and ramp up the flux, which usually means having lots of loops of wire so that your magnetic field passes through many loops of wire, right, generating lots of flux. This is a single loop circuit, and it's not necessarily going to have a whole lot of magnetic field because the magnetic field is non-uniform in this loop. So I would say to you guys that there's probably not a whole lot of back EMF generated when you close this switch or open this switch because the circuit doesn't generate very much flux. So we can probably consider the possibility of, I don't know, defining this based on its size. And the way it's defined looks like this. This is how we're going to define inductance. We're going to use the letter L to represent inductance. I guess I was used. Something about current, which is kind of funny, right? We're going to use L for inductance, but inductance starts with I. We're going to use I for current, but current starts with C. Right? You guys see it, don't you? And we use E for EMF, even though it's a voltage supply. So, I mean, there's a lot here. You can unpack it later, but we'll use L to represent inductance. And what it says is that the EMF produced will be based on the rate of change of the current in the circuit and will oppose that change. Now, we're supposed to compare this with something else, something we know quite a bit about. Capacitance is a similar process, where if we look at capacitance, capacitance is about an EMF and a storage of charge. Inductance is similar in that it's going to create an EMF, which means it's going to create a way of distributing energy. But the difference is capacitance was based on how much charge you could store. We defined a device based on how capable it was of storing charge for later use. If you look at inductance, if we want the inductance to have some kind of meaning, to be able to store energy, do you realize that for inductance to have a lot of stored energy, it's about how well it can deal with the rate of change of current, not how well it deals with the storage of charge. So this EMF only exists while there's a current, as David was trying to bring up before. And that current has to be changing for us to see the result of this EMF. Capacitor is different than that. A capacitor stores charge, and once that charge is stored, that EMF is there until the charge is taken away. But an inductor's EMF is only produced while the current is changing. So I'd argue that this is very much static, and this is very much dynamic. That we only see this back EMF while something is changing, which makes inductors a little bit weird at the start as to what they're capable of doing for us. So although they can store energy, they only store energy while there's current flowing, and we only see the EMF produced when the current is changing. That makes them a little bit more complicated in what they can do. But I also want to point out something incredibly important that should make it into your notes. How often did we use this in Kirchhoff's laws? Any circuit that had a capacitor in it? Because this represents the EMF of a capacitive circuit in the same way that this represents the EMF that we expect for a resistive circuit. These three are the way in which we deal with these electronic devices. They're how they get introduced into Kirchhoff's laws, and they describe and define how our circuit behaves. So if you'll recall, we generated the time constant and how a circuit gets charged by looking exclusively at these two inside a circuit. maybe one where we've applied a voltage from an external source and tried to see how long it takes to charge the capacitor, or one in which the capacitor is already charged and we tried to discharge it to see how long it would take. Do you remember those Kirchhoff's laws formulas? They generated some kind of differential equation that we could use to figure out how long it would, which parameters of our capacitor would determine how long it would take to charge or discharge those circuits. We can figure out a way to make an inductor, something that would generate a lot of back EMF. Now, I don't think it's going to be a surprise. This device, probably going to be something that has lots of wraps of wire and is designed to ramp up the magnetic field. How many devices have we talked about when it comes to making magnetic fields? We've talked about 4 devices. I asked for a number, 4 devices, but thank you for pointing out one of them is a solenoid. We also have the magnetic field around a current carrying wire, magnetic field for a current loop, and one more? Toroid. So of these, which of these has the potential to ramp up the magnetic field dramatically? Solenoid and toroids, those are the 2. So if we want to find a way to ramp up inductance, it's probably going to be at the expense of creating something that ramps up a magnetic field. So solenoids and toroids are probably the best way to generate something that has electronic inductance. Now, this next conversation, just please take it with just put it in your notes if I can, because to this day, none of this sticks in my head, but it needs to stick in your head. If we solve this for inductance, we get something that is negative the EMF divided by di dt. We're just solving. The units of this will be volt per amp second, or a volt second per amp. We will call this the Henry. And we'll use a capital H as the symbol of the Henry. Not to be confused with what we did for capacitor. If we talk about capacitor, it was charge per volt, which was Coulomb. Coulomb per volt, which we called the farad. So the farad is a symbol of capacitance, and we know that that's based on how much we use that to determine how much charge and therefore energy we can store. The Henry is similar. The Henry is the unit for inductance. It can tell us how much back EMF we can get and how much energy we can store. So let's talk about how we might measure and use inductance. As you said before, probably the best way to ramp up that flux would be to use a solenoid. So the symbol for an inductor looks like a little solenoid. This is the symbol of an inductor. So just looks like a bunch of loops of wire. So when you're drawing yours, please be careful. You don't want to get so haphazard that you make yours look like a resistor. The resistor's got to be the zigzaggy lines, but the inductor should show that it's like a spiral. This symbol is a symbol for an adjustable resistor. There's several different ways to draw it. This is the way that I'm going to draw for this particular instance. You will need to learn the various ways in which an adjustable resistor can be drawn. This is the most common on the AP exam, but there's at least one other that shows up. It looks like that, which just has an arrow drawn through the resistor. And then there's one that looks like this, which has 3 connecting points. So the idea here is that you can connect these 2 and it'd be a variable resistor, or you could connect these 2 and those would be a variable resistor, or you could just use it as a resistor and not use the dial at all, and you would just get the max resistance. All of these represent symbols for variable resistors. This is the most common that you'll probably be tasked with in the symbology we're going to see in the future. Now, let's talk a little bit about what's happening here in our inductor. If we consider that our inductor is indeed a solenoid, so I'm going to try and draw a solenoid here. so we kind of get a picture of it. So we're going to use a solenoid. If we close the switch on the circuit on the left and have a current passing this way, when it reaches our solenoid, our inductor, the current will be going this way through the wires. Everybody see that from the drawing I've made? What will be the direction of the magnetic field inside our inductor? And we got your little right-hand rules, all good with down. So a magnetic field will be created that penetrates club schedule today. Always got to remember, probably some meeting where there'll be a picture taken, probably. Yeah, understand. So we're assuming for this moment that we have closed the switch on this circuit and there's been the establishment of a current. So I've gone past the point where we've seen the effect of what happens when we turn the switch on. We're just making the assumption that at this moment there is a constant current passing through the circuit. Everybody okay with that? So at this moment, that means there is a constant magnetic field that is inside the area of the solenoid. And the magnetic field is based on the structure of the solenoid. All good? We're calling our inductor a solenoid, and we're using the solenoid terminology because we know that the best way to get an organized magnetic field is to do so in a group of organized coils, and that's a solenoid. Does that make sense? And also that the magnetic field inside a solenoid is pretty uniform. So it makes for a good test bed for what happens when we try to change the current in the circuit. I want to remind you that we have defined the back EMF, and I'll put EMF from an inductor as minus L times di dt, where L is a measure of the inductor's performance in units of Henrys. That's right, Henrys. All right, so here we go. So right now, there is no back EMF in the circuit. If the current is constant, di dt is constant, and there will be no back EMF. If we try to, say, lower the current in the circuit, maybe, just instead of using a switch, because we don't want to stop the current, but if we want to lower the current, we could do so by adjusting this resistor. Does that make reasonable sense? So if we say increase the resistance, we would suddenly start having a reduction in the current. The instant there's a reduction in the current, now we can do this kind of by what we know about the way these circuits work. If we reduce the current, this statement says that there will be an EMF in this direction from the change in current. It's going to oppose the change in current. And if it opposes the change in current, it's going to produce an EMF. This is the back EMF. Now, we can probably work this out ourselves. There's a magnetic field passing through the coils of this inductor. If we were to look down the range of this inductor, so let me draw the wires like this. So that we're showing the current that's in our circuit is going this way. And the magnetic field is into the board inside our inductor. Now, the magnetic field is going to attempt to disappear because we're lowering the current, right? So there has to be a EMF produced to try and continue the current. So I drew this in the wrong direction, and I am sorry. To do that, there would have to be an EMF to try and reinforce the direction of the current that we have. Right, so if we use our right-hand rule, if the magnetic field that's inside the loops, even though it's being generated by the current that's already there, should we attempt to turn down the current, then there'll be a loss of magnetic field. So that will generate an EMF because of Faraday's law that has to try and increase the magnetic field that's being lost. Does that make sense? So by my right-hand rule, that would try and produce a current that continues to be in the direction of the current that's already there. So again, if we just ramp up the resistance, suddenly there will be generated an EMF that's going to oppose the change in current, and in this case would be in the direction of the in the direction of the current that's already there. Now, this acts like a battery, adding energy back into the system. So you're trying to take the magnetic field away, energy is coming from the magnetic field to produce a current to try and prevent the change that you're attempting. That energy is in the magnetic field. So as you turn down the current, you would find resistance to that change. And I'm using the word resistance here not as a resistor, but what I mean is you would be, say, increasing this resistance, reducing the current that's in the circuit, but the current wouldn't go down right away. There'd be lag because you would be producing an EMF that would keep the current going. So it would lag behind the change you've created. Again, the inductor is going to act like inertia to your circuit. So you suddenly increase the resistance, but after a few moments, the current will then begin to change as the energy starts to dissipate out of your magnetic field and can no longer support the current that's there. That's how this is intended to be interpreted. The reverse can happen too. So let's say I instead of increasing the resistance, I decrease the resistance. The effect of decreasing the resistance will be to increase the current, right? Making the current a bigger number. If I try to increase the current, the magnetic field is still here, but when I increase the current, that's going to try and increase the flux in the loops. Suddenly, there's going to be resistance to trying to increase the flux in the loops. Now, the current's already producing this magnetic field. But as you try to increase the magnetic field in this region, there's going to be pressure placed on the current by an EMF that's going to suddenly come out of nowhere to act like a battery to try and slow down the current. Meaning you're trying to increase the current, but this EMF will suddenly be produced to try and prevent the increase of current in these coils, because it's trying to prevent the increase in the magnetic field that would be generated in these coils. So, in a sense, there is a true EMF produced, and this EMF tries to oppose the change in current. But that opposition comes from the energy stored in the magnetic field. So this is an effect of the energy in the magnetic field. Now, there's a couple things to think about here and a couple things I think are tough. Let's start with, instead of a resistor here, let's change our circuit a little bit and replace the resistor, and you might want to redraw yours, with a switch, and speak of the idea of a steady state and initial state system. Now, replacing this resistor does not replace resistance in the circuit. I took the resistor out and put a switch there so we can talk about a state before the switch is closed and a state after the switch is closed, but an inductor brings its own resistance to the circuit. So although I've replaced the variable resistor, there is still resistance in the circuit. All inductors add enough resistance to a circuit. Unlike capacitors, which generally have none of their own resistance, inductors have their own resistance. And it's the amount of that resistance that that makes a difference. So again, inductor here. The steady state condition of this circuit is a little different because we're going to start with no magnetic field and no current in the circuit. So let's get rid of all of this and consider what happens when we just close the switch. So our current condition is no magnetic field, no current, and we are at the moment before time equals 0. So t equals 0, I equals 0. Now, inductors are going to behave different than capacitors, and I think you can already see what's going to happen here. In our set of coils, right, there is no magnetic field. When we throw the switch, we're going to attempt to create a current that passes in this direction. And we've ramped up the inductance of this circuit by having an inductor placed in the circuit, something that will concentrate magnetic field. So the moment I turn this on, current is going to attempt to go this way in my loops. It's going to attempt to. But there's no magnetic field in the coils at all. We're going to try and create a magnetic field that's into the board. So immediately there is a back EMF that is produced that will oppose this change. So if time 0 is the moment you flip the switch, then at time 0, for lack of a better word, an uncharged inductor, it's not the word we will eventually use, but it should conjure up the capacitor. Because there's no magnetic field there, when you close the switch on an RL circuit, you will get infinite resistance for the inductor. It will oppose the movement of current with an EMF that matches the EMF of the battery applied. So this EMF and the EMF in your battery will be nearly equal, preventing any current from flowing the instant you close the switch. This is the opposite behavior of a capacitor. In an uncharged capacitor, it shows 0 resistance. But an uncharged, and again, that's not the right word to use here, but an uncharged inductor shows infinite resistance. It's the opposite of a capacitor. You guys follow along here? Now, the steady state condition will mean that as current begins to flow into that circuit, which it will, the moment you start getting a little bit of current into the circuit, your dIdt starts to go down. The rate of change of current goes down once the current begins to change. And we start producing a magnetic field. There'll still be some implied resistance, but this EMF, this back EMF, starts to get smaller as the current begins to develop. Eventually, after a long time, we'll get a current in the circuit that is equal to whatever the battery's EMF is divided by whatever the resistance of the circuit is. And our inductance will act as though it has 0 resistance. So if you need some quick notes for this, the inductor behaves in the opposite way as a capacitor. When there's no magnetic field, or you have full magnetic field, we'll start with the no magnetic field. When you have an uncharged inductor and you attempt to charge it, it will act as though it has infinite resistance. However, once you reach a steady state condition and it has current passing through it, when the current reaches its maximum, the inductor will have 0 resistance. Now it's going to do the reverse when you attempt to stop that current. The problem is, getting the energy back out from an inductor is challenging. And David brought up the reason why yesterday. If we break the circuit we instantaneously stop the current. And all of a sudden, the magnetic field will begin to collapse and disappear. Now, when that happens, if your inductance is large enough, you will draw sparks. You will have current pushed into the air because the collapse of that magnetic field is going to be extreme. The incredibly huge dIdt can jack up the amount of EMF enough to push current into the air, into a vacuum. So you have to be careful when using an inductor. If you want to save that energy, you have to find a way to design a circuit that will preserve the current while you're trying to use the magnetic field that's in your inductor. So one way to do that is with a special kind of switch. So I want you to imagine a circuit that might be designed to utilize the energy that's in an inductor, but do so without losing the energy in the inductor by opening a switch. With the capacitor, we could just open a switch. The energy was there because it was based on a potential difference, charge on the capacitor plates. But with an inductor, that energy is based on the current passing through the inductor, creating a magnetic field. So I got to be careful the way I draw this, so bear with me. Trying to make a resistor and an inductor and some applied EMF. And then we have a special kind of switch. All right. So this is our switch. And it's called a make before break switch. So if you can kind of tell, when the switch is in the A position, we are applying an external EMF to our RL circuit. Right, when the switch is in the A position, because when we're in the A position, our switch looks like this. So this is a condition where an external EMF is applied to our RL circuit. If we close the switch to A and we wait for a long time, our circuit will rise up until we have a constant current passing through the circuit. And that'll be I max. And at that point, our current in the circuit will be the EMF that's applied divided by the resistance of the circuit. Now, if we slide the switch over to B, you'll notice a new circuit is created before the old circuit fails. Do you guys see what's happening there? We have two leads. Now, I don't have any switches actually like this, but these, you can probably tell it wouldn't be too hard to make one of these. You just need two overlapping wires that you slide your switch across. So right here, when you're in transition, you have made the new circuit. So there's still current passing through your inductor because you're connected to the old EMF. But then you can break your connection to your EMF as you slide to position B, and now you have made the new circuit before you've disconnected the old circuit. So the energy in the inductor is preserved, and the current in the inductor starts here at whatever the current was before you broke the circuit. Remember, these are current devices, not voltage devices. Everything we did with the capacitor was about voltage. So when we took a capacitor out of a circuit, it maintained the voltage it had at the instant that it was removed from the circuit. With an inductor device, it maintains the current it had the instant the switch was moved from A to B. So it starts with this amount of current. Now, it's going to degrade rapidly, but if this resistor is a light bulb, when you make your new circuit, the light bulb stays lit because there's still current passing through the light bulb and it doesn't instantaneously go away. So I think you can imagine if you had a fully, again, wrong word, a fully charged inductor, when you make the new circuit, the bulb will stay lit as the energy in the magnetic field collapses, continuing to produce current, trying to produce an EMF in this direction to try and maintain the current and prevent the change in flux. So it's going to reinforce the current that's there. Now, how this happens, that's going to be a different story. We're going to probably have to do a little math on that to figure out how this happens. But this is the general setup of an RL circuit. So we had RC circuits before. We'll have RL circuits now. I'd like to look at both conditions. The condition when the switch is thrown to A and the condition when the switch is thrown to B. Everybody good for that? So we will assume that the switch has been at B for a long time. I think you can imagine when the switch has been at B for a long time, there's no energy in the inductor and there's no current in the circuit. Everybody good with that? So our T equals 0 condition will be that after the switch has been at B for a long time, our current in the circuit will equal 0. Okay? I'm also going to define I naught. I don't know if naught's the right word. How about I use I max to be E over R, so that when we know what the max current in this circuit will be. Is that okay with you guys? All right, we're going to throw the switch to A. When we throw the switch to A, we have created a circuit that has 3 elements in it. A simple walk around the circuit will tell me that we'll have a potential difference from our applied potential difference from the battery. We will also have a loss of potential around my inductor and a loss of potential around the resistor. And this has to sum to be equal to 0. Everybody good so far? See where I'm getting this? I'm just doing a straightforward Kirchhoff's law statement. Now, we already have defined that the EMF of an inductor is minus L di dt, and the EMF around a resistor is IR. All good? Now, this negative sign, says that it's a voltage drop. This negative sign is to tell us that the direction of the voltage is related to the rate of change of the current. They represent, in this case, the same negative sign. So when I sub in L di dt, I don't have to bring the negative sign with me because it's already supposed to be a voltage drop. Everybody understand what I'm trying to say? This is telling me that the EMF is going to oppose the direction that the current is changing. And that's what we're saying here, that we have an opposition to the EMF that's applied. Okay? So when I sub in, I'll get minus L di dt minus IR. Now, unlike with an RC circuit, this is already a differential equation. So with the other one, we had to replace current with dq dt, but because our definition for the EMF of an inductor is already a differential, this is already a differential equation. Now, that's it for creating a differential equation. It occurred the moment we subbed in the information about an inductor and a resistor. Solving it, though, well, we've solved this equation before, right? Something very similar to this, except we did it with Q and a RC circuit. Do you feel like you guys have the skills to do the rest of this, or do you need to have Mr. Shelton lead all of that again? I think you guys should have this one. So why don't you, I'll just say what you need to do. Like start out by isolating the differential. You get it to one side. And then maybe, I don't know, separate the derivative. Am I going too fast? You're likely going to need to then collect terms. Everything with I goes to di, and everything with t goes to dt. and then integrate both sides. So I get something that looks like is that kind of what you guys get? Anybody need me to do work to go from here to here? Okay. So I'm going to go through and do a few of the steps. Put that down there. I want to isolate di dt, so the first thing I'll do is move the L over di dt to this side. That'd be my first step. I'm trying to isolate di dt. I can go ahead and separate the derivative in this step by just multiplying both sides by dt. I notice there's no t in this, so I don't have to worry about moving a t to one side, but I do have an I in this, but it's kind of trapped inside these parentheses, so I'll have to take the whole term, the whole expression and move it to the other side. So I'll do so by just dividing both sides by the EMF minus IR. And now integrate both sides. Is that good? Okay, this side's just T, no work there. But the other side, you guys are at this point in calculus, right? You know how to do this. This is a U sub. So I'm going to do U equals E minus IR, du di. It's going to be minus R. So di is going to be du over minus R. All right, is this how you guys do U sub? I hope so. So I'm going to do some substitution here and get my integral of L over U times du over negative R. So that's my U sub. I'll pull out the constants just in case that they're distracting. So negative L over R, integral 1 over U du. You probably are learning to like switch your limits when you do U sub. I just put the limits in later after I put the expression back, but if you want to switch the limits, you can do so. I didn't do that. I didn't learn how to do that when I was in school. So am I okay to keep going this way? So this is still equal to T. This is going to be negative L over R natural log of U, but that's really going to be, for us, negative L over R natural log of the expression that we subbed in, EMF minus IR. And we're evaluating this from 0 to I. And that still equals T. That all okay? We just have to plug in our limits. I'm going to plug in the limits, but I'm also going to move the L over R to the other side. That all okay? So I like to collect the natural log. I don't know how you guys are learning to do this in your mathy class, but I think collecting the natural log makes this easier for me to see it. I know that you can raise both sides to the base E with it still being a difference, but it just makes sense to do it this way first. So I make mistakes when I do it the other way. Raise them both to a base of E. And I'm going to do just a little bit here. When you raise both sides to the base of E, can you see that you could write this as 1 minus IR over E equals E to the minus R over L T? Just kind of did that because I know I'm going to be solving this for I, so it makes a little sense to me to kind of separate that. If you want, we could just multiply the E straight across. It's up to you guys. How do you want to formulate this? So you guys don't seem to care, so if you don't care, I don't care. This way, all right? I'm just going to switch two terms around and get 1 minus e to the negative RT over L equals IR over E. That okay? Multiply both sides by the EMF and divide both sides by R. So E over R times 1 minus e to the minus RT over L equals I. And you see this, right? Not a surprise. We get I max times 1 minus e to the negative RT over L equals I. It looks a lot like the charging function for a capacitor, but you'll notice that this charge is based on current, not on charge. So it's not the charge ramping up, it's the current ramping up. You guys see that, right? Because I want you to be very careful. It makes it look like it's the same as a capacitor, but it's not. It's the reverse of a capacitor. Because with a capacitor, remember, it was the charge that we were talking about slowly trickling onto the capacitor in the beginning and then ramping up quite quickly until it reached its maximum and then kind of tapering off. Here the current is doing that. I mean, a couple of little things we can talk about. At t equals 0, what's the current? You see at 0? And then t after a long time is just going to be I max. Do you guys see all of that okay? Because t at infinity means this term disappears, and so we get I max. This is the current in the circuit. So if I wanted the current in the resistor, I would just multiply both sides of this by R. So consider, if I wanted the voltage in the resistor, the voltage in the resistor would just be me multiplying both sides of this by R, which, if you look at that, voltage in the resistor, that's going to be the max voltage times 1 minus e to the negative RT over L. Right? I'm just taking one step back, multiplying both sides by R, and this gives me the voltage across the resistor. So at time 0, the resistor has no voltage. In an RC circuit at time 0, the resistor would have had all the voltage. So there's no current when you throw that switch. After some time has passed, you develop current. But at time 0, there's no current. This means at time 0, the voltage across the inductor has to be equal to the voltage applied to the circuit. Right? By Kirchhoff's laws, if the voltage isn't across the resistor, it's across the other circuit element. Another circuit element is the inductor. So if you applied a 6-volt source to an RL circuit at time 0, the inductor has 6 volts, and the resistor has none. I don't want to be confusing, but this is current flow. It's not charge. Last time we did RC circuits, we kind of treated charge like voltage. Whatever the charge did, the voltage was doing. But this is current. So current flow is the result. Now, we're not going to have time to talk about the discharge cycle, but you understand the discharge is going to look very similar to what we have with the capacitor, right? We're just going to switch this to a simple RL circuit with only 2 EMFs, one for the resistor and one for the inductor. And I'm pretty confident you can see that the current's probably going to decline to 0. We're not going to get a surprise here, and I bet there's going to be a time constant that has R over L instead of the time constant we had for a capacitor, which was R times C. Remember the difference? But one thing you might want to think about is why would you use an inductor? Well, what does an inductor do? Go ahead.